Previously, we've added weights to the mesh. Now we'll be dealing with the information for the weights. We will look at storing the weights as well as accessing the weight information. When working with weights, storing the weights is very important. It allows for a more flexible workflow and it allows for a more neat and efficient rig. More importantly, I do not trust the Capture Layer Paint node. This node will work correctly, but it can occasionally have a bug where it will lose the information on the node. It is also possible to remove the weights entirely by accident on this node. For example, if you bump the option to reset the node, we can also apply universal changes with the Apply All Changes button, and this can also cause this node to break. In this scene, the Capture Layer Paint node lost all of its information. The weights from before the Capture Layer Paint node still work, but the weight information on the Capture Layer Paint node is gone. So I will replace this node and I will repaint the weights. I will be visualizing the final layer. I want to see the selected capture region. The mask will be grayscale. The symmetry will be reflective and the direction will be along the x-axis. I'll now paint the weights again. So now I've updated the weights for the pig and I want to export them. Exporting the weights for a mesh is very straightforward and I would recommend doing this with every mesh that you paint. To do this, we'll use a ROP geometry output node. I will connect this to the first output from the Capture Layer Paint node. I am going to save this as a BGO file. I will call this file pigheadweight0. The file extension should be .bgo and I will use compression with .sc. I can then save to disk and we can use this file as a cache for our weights. I now have a simplified setup for my rig. I have a file node for the weighted mesh and I have the same rig that I used previously. One thing that we may notice with the exported rig is that we have retained the point colors that were applied while we were painting. Another result is that if I remove the point color, in this case I'll do this with the attribute delete node, we will find that the texture is no longer registering properly. This is something you should be aware of, and we may want to specify how the texture and the color are applied when we're exporting this mesh. The mesh can now be tested. I will get a rig pose node and I'll get a bone deform node. I can use these to test if the weights are working properly. The bone weights work. This is because the skeleton is the same as the previous skeleton, and essentially the weights are connected to the bone names. The weights are stored in a point attribute, and this attribute is called bone capture. There are also some extra attributes. pcapped alpha is generated when painting. pcapped frame and pcapped scale root are generated by the bone capture lines node. We do not need these attributes. So the attribute we need is the bone capture attribute. This attribute is different from most of the other attributes that we will use in Houdini. Each influence will have two sections, the bone capture region and the bone capture weights. The region will store the name of the bone influencing the weight. The weight column will store the weight corresponding with that region. At the time the weights are created, the region with the highest influence will be stored first. The second region will have the second most influence, the third will have the third most, and so on. By default, we usually have 6 capture regions. The bone capture information is generally very difficult to deal with, and we will convert it into another format if we want to work with it directly. Since this data is used for deformation, it is laid out for efficiency rather than ease of use. We now have capture weights, and there are a couple of operations that we will often want to perform on these weights, and these will be performed using the capture correct node. These operations can be performed at any time during the weighting. They do not necessarily have to occur at the end of the process. We can use this node to perform a couple of operations. However, a lot of the options will not work for KineFX. I will uncheck the regions to correct and regions to remove checkboxes. These apply to the object level rigging. We can clamp values for the weights. The first slider will be the lower limit. The second slider will be the upper limit. It is, however, very rare that we'll need to limit the weights. Something that is usually a good idea is to use the renormalize weights option. It is best to have the total influences for each point to add up to 1. This is something which can be lost during the painting process. Using this option will fix most of these kind of problems. The final parameter on this node, which is probably the most important one, is limit regions. This will allow you to set the number of bones that have an influence on a point. For example, if we want each bone to have a rigid influence, we can set the influence to 1. I can visualize this using the Capture Layer Paint node. Each region will be influenced entirely by one bone, and there should be a clear delineation on each border with no blending between the colors. There are often cases where you will want to restrict the deformations. An obvious example will be a game engine, where most points will not need more than 4 influences. By default, Houdini uses 6 regions, but for facial riggings we may want to go as high as 8 regions. There is another reason to use the limit region option, and that is that the weight painting will modify which points have the most influence. If I select the mesh, we will see that the order of the weights has changed. This is because the Capture Layer Paint node does not do any sorting for the points. If we want to sort these values, we can use the Limit Region option to reorganize the weights. We have now exported our weights and we've reorganized them. We'll now want to manipulate the data. However, the bone capture attribute is not designed to be manipulated, so we'll now convert the information into a more accessible format. There are 2 nodes which we'll use to convert the bone capture attribute. These are the Capture Attribute Pack node and the Capture Attribute Unpack node. I will connect the Capture Attribute Unpack node. The bone capture attributes now have been changed into 2 attributes. These are the bone capture data and the bone capture index attributes. These attributes are all arrays and each entry corresponds with an individual region. If I limit the regions to 1, we will only have 1 influence and 1 region. The largest arrays will have 6 elements, although most will not have this many. Because we are using the capture correct, the first entry and index will correspond with the bone that has the most influence. Without this, the value of the highest influence will be impossible to predict. So we'll look at the uncorrected example. Point 3 will have the greatest influence last, this being for bone 6. The same applies for point 5, with the last bone being bone 5. After using the Capture Correct node, all my entries are listed from the greatest to the smallest. So it is usually a good idea to use the Capture Correct node before using the Unpack node. Once we have finished working with the data, the Capture Attribute Pack node will return the weights to the original bone capture format. These values can then be used to drive the deformation for the mesh. So we have 2 attributes, one for the data and one for the indices. But we do not know which bones correspond with which index. To solve this problem, there are a couple of extra attributes on this node, and these attributes are detail attributes. These attributes are bone capture pcapped data and bone capture pcapped path. I will be using the path attribute. This is a list of the bone names, and each one corresponds with the index. We can now use the data to perform operations based off the weights. I'll start off working with the standard attribute wrangle node, and the first thing I'll do is get the array for my bone names. I will be using this array to tell which bones I am working with. This will be stored in a string variable, and I'll call this data. This variable will be storing an array, and this is defined by using square braces. I'll be using the detail function to get the attribute. The first argument is 0 as this is connected to the first input. The attribute name will be bone capture pcapped data, and the index in this case will be 0. We can then use the for each loop to loop over the array. We can also use the standard for loop, but the for each loop is more concise. The first argument is a variable, and this will be a string. This will give you the value of the specific entry in the loop. The second argument will be the array which we are looping over. To test this, I'm going to print out the bone value. We should now have the names for the bones being printed out. They're being printed out multiple times as this is being performed for each point. The for each loop can be extended to also give us an index. This will be done by adding an integer variable as the first argument. I can then add this to our print statement. So that is how I'll access the index and the name of the bone. We can now perform operations based off our weights. In this case, I'll be performing the operation on the neck. I'll store the values in a float attribute called neck. This will be set to 0 by default. We will then have the for loop. I'll be getting the value for the index as I and the value for the entry as bone. We will want to make sure that we are working with the correct bone. In this case, we'll be working with the neck. I will do this with a conditional if bone is equal to neck. If the bone is the neck, we can start looking for our information. We'll be getting the final value from our data attribute, and we'll need to use the index attribute to make sure we're working with the correct bone. This index will be the same as the index for the neck. First, I'll want to find the weight index. I'll store a copy of this attribute in a variable called index. This will be an integer array. This is a point attribute, so I'll use the point function. This is getting values from the first input. The attribute is bone capture index, and we'll be getting the value of the current point with @ptnum. I will now see if this point is associated with a bone. I'll do this with if index, and I'll test for the first index with 0. We'll then see if this is equal to the neck bone with the value I. If the main influence is the neck, I will then want to work with the value of that influence. I will store this in a float array called influence. The information is a point attribute connected via the first input. The attribute is bone capture data, and we'll get this for the current point. I'll then add the primary weight from these points to my neck attribute. I will do this with if at neck is equal to influence, and we'll be looking for the first influence in this array. We can now look at the net attribute. It should be 0 for most of the points until the first index is equal to 1, when we should now have a float value. We can now use this value, and in this example I will use the scatter node. I will scatter points on the mesh, and I will raise the number of points to be 3000. The scatter can be driven by a density attribute. I'll set this attribute to be the neck value. I'm now scattering the points with density based off the neck weights. So now we should have a basic idea of how the weights are stored, how we can access those weights, and how to save those weights as a BGO file. Next, I'll look at applying weights using packed primitives.